Ever wondered how complexity springs from simplicity? Think of AI like ChatGPT. It seems to just predict the next word but repeat that billions of times, and intelligence spontaneously appears. Simple rules, massive scale, complex results. That's emergence. In this video, we'll explore emergence with the classic Langton's ant. With just a few tiny rules, this ant spontaneously draws intricate patterns. This core idea, micro interactions shaping the macro, matters everywhere, from AI to crypto, where carefully designed rules meet countless individual actions, often leading to surprising emergent dynamics. But we won't just watch it happen. We'll build it ourselves in HoloBit, your visual lab for agent-based modeling. Let's first take a quick look at HoloBit's main building blocks. First, entities such as agents, cells, or links. These are the basic parts of your world. Second, processes, which define how those entities behave. Third, data components to store and manage information. And finally, visualization tools, so you can see everything in real time. For Langton's ant, we only need a few of these. A cell for the grid, an agent for the ant, two processes for behavior, and a worldview to see it unfold. In this short video, we'll follow 3 easy steps: analyze, build, and explore, to create the model with no coding required. Ready to see it in action? Let's start by analyzing the problem. Langton's ant has 2 core parts. First, a grid of squares, where each square changes color based on the ant. Second, the ant itself follows 2 simple rules. At a white square, it turns clockwise 90 degrees, flips the square to black, and moves forward 1 unit. At a black square, it turns counterclockwise 90 degrees, flips the square to white, and moves forward 1 unit. In HoloBit, this maps naturally because it's intuitive, agent-based, and process-driven. The grid becomes a cell entity with a changeColor process. The ant becomes an agent entity with a move process. Now let's quickly shape the model. Enter the HoloBit interface. From the left toolbar, drag a cell onto the root canvas, double-click, and name it Ant World. Drag a process into the cell and name it changeColor. Next, drag an agent and name it Ant. Then, drag another process into the agent and name it antMove. These components define the logic and rules of our model. Finally, add a worldview. This is purely for observation. It allows us to see what's happening, but has no effect on the model itself. See, with just a few drags and drops, our basic conceptual model is ready. Next, let's configure the details to turn this concept into a running computational model. Before we start, duplicate the scenario and name it clearly to save our progress. Let's start with Ant World. Select the entity and click the Enter button to access its inner canvas. HoloBit uses layered canvases, so you can clearly define each entity's logic. In the Property panel, let's set the cell properties. First, set the origin to center. This ensures that coordinate 0, 0 is exactly in the middle of the grid. Next, open Appearance and change the color from the default black to white. Leave other settings as default for now. Now, let's define how cell individuals change color. Select the changeColor process. In the panel, keep the active switch off, because this behavior is triggered passively by the ant, not by the cell itself. Open Advanced Settings and keep Belong To as individual. This ensures every single grid square handles its own color change independently. Next, open Ports. Add a variable port named targetColor. Set the type to string. This means you must use quotation marks when assigning a value, like green. Why set as a port? Because the cell needs the ant to tell it which color to switch to. Now for the inner logic. Inside the process canvas, insert a compute component after the start. Name it Update Color. Then add an end event to close the process properly. Select the compute component and input the formula. Color equals target color. Here, color is the cell's property, and target color is the input port we just made. Simple as that. Next, let's do a quick test to ensure the logic works. Return to the root canvas. Select the WorldView and set its base cell to antWorld. In the control bar, click Step once. The view changes from black to white. Initialization successful. Now let's trick the cell to verify the color change. Select the process again. Turn the active switch on and set the target color default value to green. Reset the model and click Step twice. Look, the WorldView turns green. It works. But don't forget to revert the settings. Since that was just a test, turn the active switch off and clear the target color default value. Our environment is ready. Next, let's configure our ant. Select the ant agent. The type is individual, which means there is only one ant. It works perfectly for our model. Under Appearance, set Shape to Ant and Color to Red. Then, open Location, set Current Space to Ant World. Let's reset and click Step once. A little red ant appears in the center. Great. Now for the core behavior. Click the focus icon on antMove to enter the agent's canvas and center on the process. The ant acts independently, so turn the active switch on. Here is the logic. First, the ant needs to know the color under its feet. We use a find component named findCurrentCell to target the square right here and store its color in a variable named currentCellColor. Next, use a gateway to decide the turn direction based on that color. Then we branch out. Add two move components for turning and name them clearly: white turn right, black turn left. And two more call components to tell the cell to change color, named change to black and change to white. Finally, merge back to a move component, forward one step, followed by an end event. Now let's configure the components step by step. Set the start event to type timer, then keep the default settings. This ensures the process starts from the first tick and runs every tick. Next, select the find component. Set scope to current cell. In the Compute After Action formula bar, input current cell color equals this.entity.color. This saves the color of the cell the ant is standing on. Then set the gateway to exclusive condition. Add the condition. Current cell color double equals white. This creates a fork in the process. If white, go to white turn right, otherwise go to black turn left. For the white branch, select white turn right. Set the action to turn right and angle to 90. Select change to black, configure it. Owner is find current cell, which means the found entity from the find component. Call the behavior changeColor and pass the value black. For the black branch, select black turn left. Set the action to turn left and angle to 90. Select change to white, do the same. Owner is find current cell. Call changeColor, but pass the value white. Finally, for forward one step, keep the default action forward and set distance to 1, and we are done. The ant is fully complete. Let's test quickly. Using step mode in HoloBit lets you clearly see each action: turning, coloring, moving. Click, step a few times, and watch closely. It's behaving exactly as defined. We've reached a milestone. Our concept is now a functional computational model. Now let's run it continuously. After 100 ticks, we see a pattern, but not the famous highway yet. This is because our simulation is too short and the space is too small. Let's fix that quickly. First, go to Global Settings and set total ticks to 11,000. Select antWorld and expand the max X and max Y to 50. Reset and click Run. Watch closely around 10,000 ticks. There it is. The ant builds a repeating path, the highway pattern. And there you have it. You've built Langton's ant in HoloBit and witnessed Emergence in action. It's the exact same logic that shapes complex systems around us, from game mechanics to DeFi protocols. HoloBit makes these invisible dynamics visible and explorable. What patterns will you discover next? Try expanding the model. Add more colors or change the turning angles. Keep experimenting.
Thanks for watching, and see you in the next video.